In Lesson 7.5, you will be factoring linear expressions. And what that means is that you're going to be finding the greatest common factor of two monomials, and you're going to use properties to factor linear expressions. So just to remind you, the greatest common factor of, let's say, 3 and 21, the greatest common factor is 3 because 3 is a factor of 3 and 3 is a factor of 21, and it's the greatest common factor of both of them. Okay, and 14 and 16. Okay, remember that all numbers have 1 as a factor. Okay, and then itself. So these, in this case, 1 and 14, 1 and 16. But this also has 2 and 7. This one has 2 and 8. Okay, and out of all of those factors, what's the greatest? The greatest common factor would be 2. And we use the greatest common factor to reduce fractions for one application. If I had 14 over 16, I could reduce that by 2 by dividing by 2, and I would get 7/8. Can 7/8 be reduced anymore? No. So the greatest common factor is 2. So what we're going to do is we're going to use that same process, only we're going to add some variables, which is really fun. Okay, so a factor is simply a number that to factor a number is to write it as a product of factors. Okay, so I can write 14 as a product of 2 and 7. Okay, so the greatest common factor is what we're trying to find here, but we're going to be using two monomials. Okay, so we're going to try to find out what is the greatest factor for two monomials. Okay, so you can see the process here on example 1 is that we list out all the factors. 2 times 2 times x gives us 4x, and 12 is 2 times 2 times 3 times x. What do they have in common? They have a 2, and an x in common. So the greatest common factor is 4x. Let's take a look at 18a and 20ab. All the factors are listed for both of them. What they have in common is a 2 and an a. So the greatest common factor is 2a. Let's try 12. So 12 has a 2 times 2 times 3. Now you might be thinking, where did I get that? Well, it goes back to good old factor trees. 12 can be written as 2 times 4, not 2 times 4, 2 times 6, and 6 can be broken into 2 times 3. So 2 times 2 times 3. Now 28, if I do a factor tree for 28, I can do 4 times 7. 7 is prime, so I'm going to break down the 4 into 2 times 2. So 28 can be written as 2 times 2 times 7. Then we just have the c at the end. Okay, now we want to know what they both have in common. Well, I see a 2 here and a 2 here, so that's something in common. A 2 here and a 2 here, so that's in common. So the greatest common factors is 2 times 2, which is 4. Let's look at 1b. Not necessarily writing the factor trees, but just thinking about the coefficients here. What factor goes into 25 and 15? Is it 1? Well, no, because 1 goes into every number, and 1 might be the greatest common factor in some cases, but in this case, they both end in 5. So the greatest common factor is 5. Okay, now let's look at their variables. There's an x and an xy. What do they both have in common? They both have an x in common. So 5x is the greatest common factor for 1b. For 1c, I'm going to go back to the tree method. So 42 can be broken down into 6 times 7. 6 can be broken into 2 times 3. So we have 2 times 3 times 7 times m times n. Now let's look at 14. 14 is 2 times 7, and those are both prime. So I'm going to put 2 times 7 times m times n. Okay, now let's go through and find what they have in common. They have a 2 and a 7, an m and an n. So they actually have 2 times 7, which is 14, an m and an n in common. We're going to talk about some other strategies to find the GCF of monomials. One of those strategies is to write out the factor trees, and sometimes you can do them mentally, and then we'll talk about one other method when we're together in class. Okay, let's move on and go to page 317. On page 317 at the top of the page, we're talking about factoring linear expressions. So you can use the distributive property and work backwards to write an algebraic expression as a product of its factors. And so we call that factored form when we have written it as a product of its two factors. So remember, product means multiplication. You don't see it in the problem, but that's the multiplication right there. And then two factors. 4 is one factor, and 2x plus 1 is a factor. For example 2 then, we're going to take a look at factoring 3x plus 9. Okay, so we can use a model. There's our 3 x's again, and then there's our 9 1's. Okay, and then we can split that up into a visual model to break that into 3 times x plus 3. Okay, that will give us an answer of 3 times x plus 3. There's one model. Method 2 is to use the GCF. So you can write 3x as 3 times x, and you can write 9 as 3 times 3. Notice that they have a 3 in common, okay, and they have an x here and a 3 here. So they pulled out that common 3 right there, and what was left was the x plus 3 right there, okay. Let's take a look at 12x plus 7. So if you look at 12x and 7, 12x can be written as 2 times 2 times 3 times x, and 7 can be written as 1 times 7. Do you see anything in common there? No, there's no common factors, so 12x plus 7 cannot be factored, okay? I'd like to show you just another way to do these at the bottom here, just thinking about these, maybe without doing tiles, but just thinking about what goes into 4 and 28. You might be thinking 1, but there's a higher factor. You might be thinking 2, but there's even a higher factor than that. 4 actually goes into 4 and 28. So what we're going to do is we're going to pull out that greatest common factor, the 4, and then we're going to do parentheses. How did I get from 4 to 4x? Well, I multiplied by x. How did I get from 4 to 28? I had to multiply by 7. So my answer is 4 times the quantity x plus 7. Well, let's just double check. What's 4 times x? 4x. 4 times 7, 28. Let's try that with 2b. 3 and 33. What's the factor of 3 and 33? If you said 1, you're correct, but that's not the greatest factor. 3 is actually the factor for both, greatest factor for 3 and 33. So 3 fits into 3 one time. So 3 times 1 is 3. How many times does 3 go into 33? If you said 11, that's correct. We're just going to tag that little x on the end, and we're going to double check our work. 3 times 1 is 3. 3 times 11x is 33x. Finally, on 2c, 4 and 35 are not prime numbers, okay, but they don't have any common factors, so we call those relatively prime. So we are just going to say that it cannot be factored for 2c because there's nothing we can pull out of 4 and 35 to factor it. Okay, still might be a little bit sketchy for you on this factoring. I promise we'll do a lot more of it together in class. Looking at example 3, there's just a story problem there, 2 of them. Okay, and the expression it gives you there, it just wants you to factor it. Okay, so finding again what goes into each of those numbers. So you can do the factor tree. That's 2 times 6, and 6 is 2 times 3. So it's 2 times 2 times 3 times x for 12x. 480, okay, we'll break that down into 2 times 240. 240 is 2 times 120. 120 is 2 times 60. 60 is 2 times 30. 30 is 2 times 15. And 15 is 3 times 5. Okay, so we have 1, 2, 3, 4, 5. 2 times 2 times 2 times 2 times 2 times 3 times 5. What do they have in common? They have a 2 and a 2 and a 3. What's 2 times 2? 4. 4 times 3 is 12. Okay, so we're going to pull out what they have in common. In this case, they have 12 in common. Well, how did I get from 12 to 12x? I just multiplied by x. So 12 times x is 12x. Now let's see how many times 12 goes into 48. 12 times what is 48? Well, it happens to be 4 for 48, so plus 40 would be the answer there. So 12 times x is 12x. 12 times 40 is 480. So for 3a, to factor that, it's 12 times the quantity x plus 40. Okay. In 3b, what's to put down $100 towards a new computer, will pay it off in 6 months. Y is the monthly payment. What expression represents the total price? So here's the monthly payment. We're going to multiply that by 6 because she wants to pay it off in 6 months. And we're going to take away the $100 because that was the down payment. So let me just check on that. Actually, it's plus $100. Right, that makes sense. Sorry about that. So 6 times the number of payments, Y, plus the $100 you put down, should be the total cost of the new computer. And then up here we had the right answer there. So again, we'll do a lot more of these in class, practice together. You also have homework, practice 7.5, and a couple IXL lessons to practice this concept of factoring linear expressions.